granted. This begins EE 544 on Thursday, April 17th, 2014.
Good afternoon, everybody. Let's continue our discussion from last time. We started talking about mixers, and we said that a mixer is a nonlinear device, which means what? It means that when you design a mixer, you need what? You need to have at least a what? A nonlinear device in the system. You cannot design a mixer with just what? Passive components. There must be a nonlinearity in there. There are two types of topologies that we will be discussing: nonlinear mixers and what? Multiplier mixers. Multiplier mixers. Another name for multiplier mixers we will see is what? Is a current switching mixer. We'll see what current switching is in just a second. Mixers, by the way, could be active mixers or what? Passive mixers. Passive mixers will not provide you with any what? With any gain. Active mixers will provide you with what is known as a what? Conversion gain. And how did we define the conversion gain one more time of a mixer? Is the what? If we are to conversion gain, if you are talking about what? A voltage gain, then it's the what? It's the RMS voltage at the IF port divided by what? The RF voltage at the RF port. If you are talking about power, then it's what? It becomes the what? Square. And keep in mind that the voltage gain, conversion gain, and the power conversion gain need not be what? The same. It depends on what? It depends on the loading at the input and at the output. But if the load, if the same resistance both at the input and the output, then the ratio will be what? Will be the same, because instead of using 10 log, you are using what? 20 log. But that's because it's squares, or 20 log, same thing. Yes?
In case of the nonlinear mixer, do we have the single balanced and double balanced, or is only for the multiplier mixers?
No, it's for both, as I will show you in just a second. The question is what? When we talk about single balanced mixers and double balanced mixers, this applies to what? This applies to situations when what? What is a single balanced mixer? A single balanced mixer is when what? When we do have what? When we do have either the local oscillator or the what? Or the RF leaks into the what? Leaks into the IF port. Clear? It leaks into the RF port. We might have more than one. But you will see, by the way, most of the time the mixers are used as the what? As the multiplier type mixers, which I will show you in just a second. Clear? Okay. Now we started. This is from last time. I just brought the notes from last time. We started looking first of all at the nonlinear circuits. In a nonlinear circuits, we are using what? You are using a nonlinear device. One of them is a what? Is a transistor or the MOSFET. In a MOSFET, we know that when we drive the MOSFET into saturation, the relationship between the current and the voltage is what? Is a square law device. And that's what we want, a square law device. Clear? Okay, so we use this one. The problem with this one, again, with the nonlinear design, is that the input to the nonlinear system, is actually what? The sum of the what? The local oscillator plus what? Plus the RF. Now, when you do the sum, it means what? They are in the vicinity of each other. The isolation between them will not be what? Will not be the best. Did you get my point or not? Now, we will see how that is different in the case of the switching or the time varying mixers. Okay. The circuit here is a very simple circuit. This is what? This is a transistor. You need to operate it in the what? You need to operate it in the saturation region, which means what? This one is behaving as a pure transconductance, current source, constant current source. Clear? And you are applying the input, which is what? VRF plus VLO plus what? V bias. Now, what is the VGS? What is the VGS? VGS is equal to what? VRF cosine omega RF, VLO cosine omega LO plus what? V bias. Are you following me or not? Okay. When you are going to put what? All of these in here, and when you square it, what are you going to get? You are going to get all types of what? All types of components. This one, the tank circuit, will what? Will reject all of these components and what? Leave the only component of desire, which is what? Which is the omega LO minus the what? Omega RF, or vice versa. Omega RF minus omega LO, depending on whether it's high side or low side injection. Clear? Clear? Just a simple transistor. Now, we saw that in order to improve on the isolation, in order to improve, by the way, where did I get this? Can you tell me where did this come from? GC equal to what? Mu COX W over what? 2L ALO. Where did this come from? The GC. How do I calculate it? Can we prove this one? What do I do? In place of the VGS, what am I going to plug in? I'm going to plug in here. In the notes here, this is VLO. In here, it is what? ALO. So the ALO is the same as what? Is the VLO. Yes? No response. Yes or no? Okay, you plug it in this equation, and then you retain only that component. You will see that when you divide this component by the what? By the voltage at the input, which is what? By the way, what are you dividing it by? You are dividing it by VRF. Did you get this or not? You will end up with GC equal to what? Mu COX W over what? 2L ALO. Let me make one comment. Please hold your question. One comment. Are we getting gain from here? We are getting gain, but the gain will depend on what? The properties of the device. Properties of device means what? The width of the device, the length, and so on. The smaller the length, what will happen? What will happen is that the gain will become what? Will become higher. The larger W is, what does it mean? It means the gain becomes what? Becomes higher. The current becomes higher. Why? Why? The resistance that is experienced by the what? MOSFET is inversely proportional to the what? To the aspect ratio. Aspect ratio is what? Is W over what? Did I mention that before? No, maybe I did not mention. W over L is called what? The resistance of the MOSFET is inversely proportional to the what? To the omega over L. In other words, the larger the omega L is, the smaller is the what? Is the resistance, which means what? The current will go higher. Yes?
You have to find the gain of the mixer. The equation there is for the current, the IDT. Do we need to find the voltage out of it? Then we divide by the RF?
The voltage is the R, the resistance. The load, you just multiply it by what? By R. I did not get your question.
What I'm saying is that to find the gain of the mixer, we divide the voltage out, which is voltage of IF, by voltage of RF.
I know the voltage at the output at the IF is just simply the current times the load, times whatever the load here, R. Yes or no? That's Ohm's law, just Ohm's law. But make sure that you take the what? You take that component, which is what? It's as the IF. It's the IF component, which is what? Omega LO minus omega RF, or the other way around. There will be many components in here. All of them, ignore them. Just concentrate on what? Just concentrate on the omega RF minus what? Omega LO component, or vice versa. By the way, you notice that there will be definitely be equal to what? There will be some term which has what? VRF in it. So that it will cancel. See, because this one, you can see that it does not depend on what? Does not depend on VRF. So the VRF definitely what? Will get cancelled out.
And the load resistance will not be in the picture for the gain equation?
If this is the current, you are going to multiply by R to make it voltage. This one is already what? Is already written as a GC. I'm not getting your question.
Well, I'm saying that why the resistance load is not showing in the gain equation? Why it's not there?
No, I'm assuming that these are voltages already. So, I mean, you know, this is voltage, and the other one already canceled. This is voltage, it's ALO, is a voltage. Clear? Okay, good. Now, one other way that we discussed last time is when we apply the local oscillator here, and we apply the RF here, we will be able to to provide a better a better isolation between the two, because we are going to have we are going to have two transistors in the middle. But if you do have two transistors, you need to make sure that you are going to be able to to bias both of them accordingly. Both of them needs to be working in the in the saturation region. One cannot be on, the other one is off. Did you understand what I just on that? Otherwise there will be there will be nothing at the output. Clear? Okay, good. Now, before we get to the multiplier base, then what did we go? We went and discussed some passive mixers. Passive mixers means what? Those mixers that will not provide you with any with any gain. Clear? Will not provide you with any gain. Now, most of them are based on diodes. But they don't need to be based on diodes. They don't need to be based on diodes. In a minute, I will show you some types in which that they use transistors instead of the diodes. Okay, but let's first of all understand it a little bit. We went into one example. What do I have here? The VRF. By the way, where is this coming from? This is coming either from the output of the LNA or the output of an image reject filter. That's the RF. Notice, by the way, when I'm sketching it this way here, what does it mean? It means that the LNA, let's assume it's cell NLA, is it what? Is it single or double? Single. Why? Because I'm getting I'm getting only I'm getting only one polarity. In here, what did I do? I split it using a center tapped transformer. Did you get this or not? Now, in here, this one is is 1-to-1. Here also is is 1-to-1. Did you understand that or not? In other words, the number of turns here and the number of turns here is both ones. Which means what? But by the way, what is the total number of turns here? Total number of turns here is twice. The center points is 1. And I'm going to put the VLO here. That's the VLO. The VLO is connected to the ground. And again, as I told you last time, the diodes are in opposite directions, which means one of them is one of them will be in the forward bias, the other one will be in the in the reverse bias. The VLO is the dominant voltage that determines whether the diode is forward bias or whether it's reverse bias. The reason for that is that because this one is 1-to-1, then this VRF will be the same as the VRF here, but the VRF will be in general weaker than than the VLO. So the VLO will be the prominent term. Now, what is the voltage here between this point and this point? It's VLO plus VRF, which is exactly the same concept that we had here. It's a VLO plus a VRF. Did you get my point or not? It's exactly the same concept, and that's why I told you whether you use transistor or whether you use diode. Oh, so you have this. In the positive going edge of the VLO, in the positive going edge of the VLO, what can you tell me about this diode? This diode is is forward bias, whereas this diode is reverse bias. Notice, by the way, the voltage here is is VLO minus VRF. Do you agree? But the VRF is negligible, again, as I told you, compared to the VLO. So the VLO is on the negative cycle. On the negative cycle, on the positive cycle, it means this one is this diode is reverse biased. Did you get this or not? Reverse bias means it's an open circuit. So the only current that comes is is this current. What is the voltage? What is the output voltage? The output voltage is is the current times the times the RF. Clear? So what do I have? I have the output voltage is the is the VLO plus the plus the VRF. But remember, this is the voltage only when there is a only on the positive half of the cycle. In the negative half of the cycle, it's it's the other way around. It's VLO minus VRF, because it's this one. On the negative half, this one will be forward bias, whereas this one will be reverse bias. Just the opposite. Clear? Now, if I want to group equation 1 and equation 2, I write it this way. V out of t equal to VLOT plus VRFT times times S of t, where S of t is a it's a square pulse bipolarity or biphase. Biphase means double polarity, plus 1 and it's minus 1, because this one is plus or minus Then what did I show you last time? I showed you that then since this is a periodic signal, I can represent it by what? By a Fourier series expansion. Yes? Now, at what fundamental frequency here? What is the fundamental frequency here? The fundamental frequency is the same as the what? As the LO. Why is it the same as the LO? Because LO is the dominant Y. And the VRF is what? Is negligible. Did you get my point or not? The VLO will depend whether it's what? Whether a diode is reverse bias or whether it's a what? Forward bias. Clear? Okay. So what do we get? We get V naught, this is from last time quickly, V naught of T equal to what? VLOT plus what? V cosine 2 pi R of T. This is what? What is this? This is the R of voltage, yes? Times what? Times S of T, which is what? Which is the square pulse device. Clear? Clear? Okay. Then I represented the S of T by what? By, you all recognize this. Do you recognize this? Notice, by the way, first of all, is there a DC component? There is no DC component. Yes or no? Cannot hear you. Okay. The fundamental component, is it more than 1? It is more than 1. Why? Because it's what? 4 over what? 4 over pi. 4 over pi is a little bit more than what? More than 1. Yes? Okay. All of this you are going to multiply by what? VRF. Now, I want you to understand one thing. Since this one does not have a DC component, will I get an RF component at the output? By the way, when I say V naught of T, what does it mean? That's the what? That's the IF. So instead of writing the V naught of T, if you want to write it as what? V IF of T. Would you get an RF component? You will not get an RF component. Will you get an LO component? You will get an LO component from which term? From this term. Did you get this or not? Okay, so when you do that, VLOT, now which component am I interested in? Which of these sum? Is this an infinite sum? That's an infinite sum. Which one am I interested in? N equal to 1. So what do I do? This is N equal to 1. What do I get? FLO minus F naught. What is the amplitude? It's 2V over what? N pi. That is what? That's the peak voltage. The peak voltage at where? At the fundamental component at where? At the output. The fundamental being what? The IF. Did you get this or not? Now, what is the input voltage? The input voltage, which is at RF, it's what? V cosine 2 pi R of T. What is the maximum? V. So if I divide this one, 2V, where did this, by the way, is this conversion gain? Is it a voltage or is it a power? Why? How do I know that it's a power? Because you can see that I am what? I'm squaring. I'm taking the RMST. Yes or no? It's the average powers, ratio of the average power. Clear? By the way, what am I assuming here? I'm assuming that it's the same what? The same resistances here. So I don't worry about it. Clear? The resistance will cancel. Okay, and what did I end up with? I ended up with 4 over pi squared, which is what? Which is minus 40 dB. Minus 4 dB. Now, minus 4 dB means what? Means if you take 10 log 4 over what? Pi squared, you will get approximately what? Minus 4 dB. No gain, just losses. Did you get it or not? Yes or no? Okay, 1 second, hold this. Okay, yes, sir.
For isolation or with isolation in this active?
No, this one also is for isolation. All of them, whenever you are going to put what? Whenever you are putting the VLO and the VRF, by the way, is this one being what? Being transformed to this voltage here. So in other words, whatever in here, whatever any distortion here or some degradation or something will be what? Will be mapped to here as well. Distortion, isolation is a big problem. You need to worry about it, and we'll see how that is done in the case of the switched mixers. Let's take one more example. There are actually 3 examples. I will let you worry about the third one yourself. Let's look at the second example. What do you notice? The diodes. Both are what? Both are in the same direction. Now, this is exactly the same situation. So this is the VRF. This is what? Center tapped. It's still 1 to 1. Yes? But look at the output. I want you to compare this with the previous one. This is the previous one. The output here, they were what? Connected together to the what? To RL. In here, the output is what? Is going to another transformer, which is also center tapped, and the output, you take it from what? Separate transformer here, from the primary. These are secondaries, this is a primary. Did you get, when you look this way? Did you get my point or not? Yes? Can we analyze it? That's very simple to analyze it. Again, what is the input voltage here? The input voltage here is what? Is VLO plus what? VRF, and let's assume that the VLO is the what? Is the dominant one. Exactly the same assumption. So, let's see if you can help me here. If this is VLO, which is what? On the positive side, on the positive cycle, what can you tell me about this? This one is forward bias. What can you tell me about this? This one also is what? Is forward bias. Now remember, this voltage is what? Is VRF plus VLO. This one is what? VRF minus VLO. Yes or no? Okay, which means what? Which means that the VLOs will what? Cancel, and I end up with what? V out of T. What is the V out of T? Again, from here, what is it? It's VLO plus what? VR of T minus VLOT plus what? VR of T. Do you understand why the minus sign here? That's the minus, because this one also is what? Is center tapped in here. Did you get this or not? So from here, what do I end up with? I end up with V naught of T equal to what? VR of T. I'm not sure. Did you get this? Did you get this or not? And here I have voltage from both sides because both of them are what? Are active. Both of the diodes are active. So you are going to what? You are going to add these. This one will cancel and you end up with what? VRF. There's a factor here. You put 2 or 1/2. Doesn't matter. This one, by the way, is also 1-to-1, 1-to-1. So you will get exactly VRF. Did you get my point or not? This one is split, but this one is split the other around. So what you get here is the same as the voltage in here. Clear? Okay. Now, what does that tell you, by the way? The V out, remember, the VO out, the VOT is what? Is the output at the what? At the IF. This is, in other words, this VOT is what? VIFT. Clear? What is it in this case? VRFT. Same thing. Now, if VLOT, which is the negative side means what? This is the negative side. What can you tell me about the two diodes? They are both what? Cut off. What is the output voltage? 0. Yes or no? So what does that tell you? It tells you if you want to combine these two situations together, what are you going to get? VOT, which is the what? Which is the IF voltage, equal to what? VRFT times what? P of T. But now this P of T, is it a plus or minus 1 or is it 0 plus 1? 0 plus 1, which means what? It looks like this. Yes or no? Again, at what rate? What is the rate of this square pulse? It's the same as the what? As the omega LO. Has the same rate, which means what? The period. The period of this guy is what? Is 1 over what? FLO, or 1 over omega, 2 pi over omega, whatever. Clear? Clear? Okay. Now, can I represent this by a Fourier series? I can represent by a Fourier series. Well, I get a DC. When I get a DC, when you multiply it by VRF, what does that tell you? It tells you that the RF will show at where? At the output. Is this still a single balanced? Still a single balanced. Remember, single balanced mixers, either the VLO or the what? VRF will show up in the what? In the output, but not what? Both. If they are not, if both shows up, we call it a what? An unbalanced mixer. If none of them shows up, which is the best thing, we call it a what? We call it a double balanced, which I'll show you in just a second. Did you understand where this equation came from? The output is either what? VRF times 1 or what? 0. Why the 0? In the negative cycle of this guy, both of these are what? Open circuit. Open circuit means what? Means it's not conducting. Clear? Clear? Oh, so I represent this one by this one here. Notice, by the way, in here, am I getting advantage? In other words, is the fundamental, in this case, higher or lower than a sinusoid of the same? This one is lower. Why? Because it's what? 2 over what? Pi. 2 over pi is less than what? It's less than 1. The other one was what? 4 over what? Pi. And we got an advantage because 4 over pi is what? Is a little bit more than 1. Did you get my point or not? Okay. So I represented by a Fourier series. This is what, by the way? This is the, by the way, can you tell me what is this sign? Let me ask you a question first of all. Are we going to, what kind of harmonics are we going to get here? This one is like this. Do you notice only cosine? I do not get what? Sine. Why? Because this is what type of a function? Even function. Which means what? In the Fourier series expansion, there should only be what? Cosine. Because if there is a sine, we know that the sine is a what? It's an odd function. That does not match. Yes or no? So all of it is in the cosine. By the way, what does this one look like? Sine n pi over 2. What does it look? Sine n pi over 2 divided by what? N pi over 2. That's a sinc function, which means what? By the way, is this a solid sinc or a dotted sinc? Do you understand, first of all, what a dotted sinc means? Or is it a solid sinc? It's dotted sinc. Why? This is the Fourier series expansion. And the Fourier series expansion, the frequencies are only either at what? The fundamental or integer multiples of the fundamental, which means harmonics. This is not a Fourier transform. It's a Fourier series. It's a periodic signal. Clear? Okay. So I multiply this. I get this. This is the RF component that is what? Fed forward to what? To IF. Did you get my point or not? Yes or no? It's fed forward to IF. Again, the reason for that is just because of the terms. All the terms except what? FLO minus F0. All the terms here. How many terms, by the way? Infinite number of terms. All of the terms, they will be what? They will be filtered out using a what? Using a filter at the output. Did you get this or not? Question. No. Question. My question first comes before you. What kind of a filter? Low pass, high pass, what kind? That's a band pass filter. For what? For heterodyne, super heterodyne. But if it was a what? But if it was a homodyne, then it becomes a what? A low pass filter, because the spectrum will be centered around the origin. Did you get my point? Yes. Yeah, hold your, one more. Then what do I get? I get the convergent gain. Which component I take? I'm still waiting. I'm taking the n equal to 1, so it's what? V is this voltage. V over pi square. Why am I dividing by 2? And that's the power, the RMS power, the average power. Okay, and divided by, where is this coming from? That's the input. It's V square over 2 is the average power of the sinus. Did you get this or not? Of the RF signal. The V square cancels. I end up with what? 1 over pi square. By the way, is this better than the previous one or not? Well, this one is worse. Are you following or not? This one is worse. It happens to be what? 1 over pi square. But regardless of whether it's what? Better or worse, these kind of mixers is not going to provide you with any what? With any gain. These are passive mixers. The beauty of them is what? Is they are cheaper than what? Cheaper than the active mixers. Did you get this or not? And again, as I told you last time, for mixers, more important to worry about is the what? Is the linearity and the what? And the noise figure rather than the what? Rather than the conversion gain. You are going to get conversion gain from subsequent devices or what? Previous devices, from the amplifiers and so on and so on. Clear? By the way, the IF, when you design the IF stage, you can have what? Multiple IFs. Multiple IF stages. So each one of them will contribute what? Part of the gain, part of the gain. The overall will be whatever you design. I'm very sorry, my dear. Your turn right now. I will shut up. I know that. Yes?
F0, is it the same as the frequency of the RF?
F0. Where F0? Where do you see F0?
L1 minus F0.
Oh, sorry. This is a typo. This one. It should be what? R? F. Which, when I say F0, it means what? The center frequency of your channel. Of your channel, which is what? Which is the RF frequency. F is F0. But you are right. I need to be consistent. So, by the way, every FLO here, every FLO, no, sorry, every F sub 0 is what? Is the FRF. Did you get this? Do I need to change in everyone or did you get it? Okay. Now, did you get this one? Now, the next one, I will not go through it. I will let you think about it at home. This is what I suggest. Do not look at the solution. Do not look at the derivation. A simple derivation. Derive it yourself. Are you following or not? And what do you notice? First of all, what do I call this configuration? You have seen it before or not? That's a bridge diode. Are you following or not? And instead of using what? 2 diodes, I'm using what? 4 diodes. Are you following or not? Now, I want you to notice this one and this one are what? In other words, they are what? When you see, let's assume this is positive. Let's assume this is positive. What does it mean? This one is on, Are you following on that? Now, notice, by the way, if this is positive, this one will be negative, which means what? This one will be what? Off, which means what? What does it mean? It means this is the path that you will get. This, will this one be on? This one will be on. Are you following on now? Whereas this one and this one will be what? Will be off. On the negative cycle, which one will be on? Which one will be on? This one will be on, and this one also will be on. Whereas this one and this one will be what? Off. Clear? You sketch the equivalent circuit. I said I'm not going to show it to you. Apparently, I will show it to you. But I wanted to see where are we getting the output. The output, we are going to get it from a center tap of a what? Of transformer, not from here. This is where we are going to apply the what? The VLO. This is where we are going to apply the what? The VRF. Both of these, by the way, are what? Are 1-to-1. Clear? So, let's see if you can tell me the equivalent circuit. Where did I get this? RD, by the way, is the what? Is the small resistance of the diode when what? When forward biased. When forward biased, R of D is the what? Is the small resistance of the diode. By the way, in the final answer, when you derive it, in the final answer, you can say let R of D equal to what? Equal to 0. Negligible. Did you get my point or not? Yes or no? Now, when it is reverse bias, you are going to assume that the diode are what? Are open. Explain to me. If VLOT is positive, is positive, which means what? The positive cycle. What can you tell me? D2 and D4 are what? Conducting. Why? Why? If VLO, this is the VLO, not the VRF. And remember, it is the VLO that will determine what? Whether the transistors are what? Operating or what or not. Because the value of VRF is negligible as far as the VLO is concerned. If this is positive, what does it mean? It means this one is positive. So what do you tell me? D2 will be what? Active. Who else will be active? D4 will be active. Whereas D2 and D3 will be what? Reverse bias. What will the equivalent circuit be? Let's see if you can tell me. This is the equivalent circuit be. Okay, what is this? This, the center tap, is connected to what? RL to the what? To the ground. This is this one. This is the center tap. Do you see this center tap? And this is the ground, and this is the what? RL. And I'm measuring the voltage here. Yes or no? Cannot hear you. Okay, what are these? Can you tell me what are these? VLOT, VLOT. This is this one. This and this. Did you lose me? One more time. Where is this one? Just this one. This one is this one. Only this one. Clear? And where is this one? This one is this one. Now, in the center tap, what do I have? I have a resistor to the what? To the ground. Yes? Now, where is the VRF? Where is the VRF? This one is grounded, which means what? This is the ground. The VRF is what? Is from, is from the ground. Yes? It goes where? Resistance. This is the R of D. R of D is back to what? Here. Clear? Clear? Okay, and you write the equation, by the way. How many loops in here? How many loops? But what, by the way, why do we have two RDs? We have two RDs because there are two diodes that are going to be what? Active. Yes? So this is the RD, this is the RD. Yes or no? Okay. This, the current here is what? I1. The current here is what? I2. What is the current in RL? What is the current in RL? The current in RL is what? It's I1 minus what? I2. You write I1 and I2 in terms of what? In terms of the voltages. Did you say that? Yes or no? So let me see if you can help me. Where did this equation came from? Can you show me where the equation came from? 1 second, 1 second. Can you tell me where did it came from? There's a VRF in this direction. What is it equal to? I1 minus I2. Why is it I1 minus I2? I1 is going this way. I2 is going what? That way. So it's I1 minus I2 times what? RL minus what? VLOT plus what? I1 times what? R of D. I1, when the current comes in here, this one is in which direction? In this direction. Did you get this or not? Do you understand why is this one minus? Because this one is what? In this direction. But the voltage here is in which direction? The other direction. So it's minus. Did you get this or not? Yes or no? Did you lose me here? You lost me. What is the thing that's bothering you? Tell me what is the thing that bothers you so that I try harder. What, the signs? You mean the plus or minus? Okay, this one is not, it's not that hard to figure. You can figure it out yourself. Okay, now, and then what? And then you get this equation, which means what? V naught of t equal to what? Equal to this one. Similarly, when VLOT is what? Is negative, which one will be on? When VLOT is negative, when this one is negative, which means what? This voltage and this voltage is more negative than this one, which means what? This voltage will be more negative than this one. Did you get this or not? Which one will be on? D1 and what? D4, whereas D2 and D3 will be what?
D1 and D3.
Huh, I messed up? D1 and D3, I'm sorry. D1 and D3 will be what? Will be on, yes? By the way, you could tell this by experiment. Why? Because the current is like this, follow me. Here, it needs a return path. Where is the return path? Here. Did you get it or not? Okay. And you write the equations again for this one, and then what? And where is this coming from? Can you explain to me why did I bring this one again? Because again, the output is what? The output is here, this one. If what? If the VLO is what? Positive. Here, the output is the VLO is what? Is negative. So we have what? Double polarity. That's why I explained. That's why we got back to the 4 over M pi. Clear? Okay. Now, in the final equation, you put RD equal to what? 0. The RL will cancel, and we end up with exactly the same value that we got earlier. Yes? No response. Okay. But what do you notice here? Do you notice something? No. What does isolation means? You see that there is neither what? An RF component, nor a what? An LO component leaking into the what? Leaking into the IF stage. Did you understand that or not? Look at the IF equation. This is the IF. This one is the IF equation. Is there an RF component? Is there an LO component? The only component is what? Is FLO minus what? Minus F naught T. Notice, by the way, all of these components in here are what? Are going to be filtered by some kind of tank circuit that you will use it. And always remember, always put the tank circuit is better than to use a load. And you what? You make sure that the tank circuit is tuned to what? To FLO. No, FIF. I'm sorry, FIF. Clear? Oh, now, this is again, what do I call this one? I call it a what? A double balance, because it's what? What is it? Double balance, which means what? Neither the LO nor the RF is going to leak into the IF. What is this? No. Can you tell me what is this? Is this exactly the same as the previous one, the diode base? But I replace a diode by a what? A transistor. Now, what am I making sure? I am making sure that controlling the gate, one of them is a what? LO bar. The other one is a what? Is an LO. Are you following or not? Which means what? It means that, what does it mean? It means that when this one is what? On, this one will be what? Off, and so on, so. Let me ask you a question. I'm not sure how many of you took 477. Anybody taking 477? 470. Let me see if you can answer me this one. Is this a transmission gate? Did you study transmission gate? Is this a transmission gate? Why? Correct answer. Why? There will be what? I didn't get it. There will be two what? These are two transistors, one on the other. These are two transistors. You are not answering the problem properly. In a transmission gate, those two transistors are what? Complementary to each other. Complementary means what? Means one of them is an NMOS, the other one is a what? Is a PMOS. These are both what? These are both NMOSs. In a transmission gate, either both transistors are what? On or what? Off. In here, no, it's one of them is on, the other one is what? Off, and so on and so forth. Clear? Clear? Okay. you notice, by the way, this is besides the point, but in a transmission gate, when we said either both transistors is off or both are on, this is not a very accurate statement. Why? Because as you will see in 477, if you take 477, you will see that the NMOS passes a strong 0, but a weak 1. Whereas the PMOS passes a what? A strong 1, but a weak what? 0. So there comes a point in which in a transmission gate, one of them will remain conducting, but the other one will get what? Cut off. But that's only for a what? Short period of time. Clear? But I don't want to get into this. This is a totally different course. Clear? However, I do advise you is that even if you like to work in the analog, in the RF, it wouldn't hurt to take courses in what? In digital design. Do you understand that or not? For one thing, which is most important, is that remember the trend. The trend is to try to push the baseband processing or the digital processing closer to who? To the antenna. Are you following me? You are trying to replace what? You are trying to replace a large sum of what? A large sum of the processing from the analog side to the what? To digital side, so that you can use the power of the what? Of the signal processors. Clear? So, just in case. What does this look to you? Does it look to you like the bridge diode? But it's instead of what? It's a bridge what? A bridge transistors. And I will assign this one for homework. It's the same idea. Again, how many are, by the way, you notice the input? LO, LO, LO bar, LO bar. And this is the IF. I'm taking the IF from here. Notice, by the way, if LO is positive, then what do I have? Show it to me. If LO is positive, where is the circuit? Look at my finger. It will be like this. This, on, IF, this. Did you understand what I just said or not? This one and this one will be what? Off. Now, in the other half, what will it be? Follow me. This. Did you get it or not? I will assign this one for homework. But it's the same analysis. It's just exactly the same analysis. Are you following me or not? Clear? Okay, good. Now, let's get into the second type. The second type of what? Of mixers. First of all, let me, before we get to the basic idea, let me show you the circuit so that you understand what I'm talking about. We'll get to all of this in just a second. Notice, by the way, whenever you hear the word balanced mixer, if you don't see the word double balanced, it means they imply it's a what? Single balanced. Do you understand? Double balanced, you need to specify that it's a what? A double balanced. Before we get into the detail from the set of charts and from here, I want you to understand the basic idea behind it. The basic idea behind it. I have two transistors in a differential mode. Is this a differential mode? Differential mode where I am going to apply the local oscillator in a differential mode as well. What does that mean? It means that if this one is on, this one will be what? Off, and vice versa. Why? Because I am looking in here, this is the input, whereas in here is this the input. Did you get my point or not? Yes or no? This is in a differential mode. By the way, if your local oscillator, which we'll talk about next, is generating a what? A single-ended, then we need to use what we refer to as what? The balloon. Are you following me? With the one that will change it to what? To the balance case. Did you get my point or not? Okay, good. Now, I want you to understand one thing. Where is the RF getting? The RF is applied to this transistor. This transistor is acting as a constant amplifier. A constant amplifier, I cannot believe I said that. At a constant what? Current. Which means what? This transistor is driven to where? To the saturation, where the current is what? Constant. Which means this one is behaving as a what? Constant current source. Did you get this or not? Yes or no? Okay. Notice, by the way, what is the current here? I will get to it in just a second. There is an RF current here, but there is also a what? A biasing current. This circuit is not showing you the biasing current because it's only concentrating on the AC analysis, not the biasing analysis. We'll see the biasing in just a second. Are you following me or not? Now, what is the VLO is doing here? Listen to what it's doing. The VLO should be strong enough to steer the current either this way or what? That way. The same current either go this way or what? Go that way. Did you get this or not? Not both. Why not both? Because when this one is on, this one is what? Off, and vice versa. So the current either comes this way or it comes what? That way. Did you get my point or not? Now, I want you to see where are we looking at the output. We are looking at the output between these 2 points. Could I pick the output from only 1 point? Could I pick the output from only 1 point? I can pick the output from 1 point. That is a what? Single-ended. Did you understand what I just said or not? I am picking the output as a what? As a difference between voltages. Did you get my point or not? Now, in this case here, I prefer the what? The VLO to be a what? To be a what? A square law device, which means the oscillator, instead of generating a what? A sine wave, it is generating a what? A two polarity, excuse me, two polarity square wave. Did you get this or not? Yes or no? And I need you one more time to understand is that these transistors are not going to be what? On at the same time. One of them will be on, the other one will be what? Off. And this one should be what? High enough, high enough to steer this transistor from which mode to which mode? From the off to the triode. Did you understand what I just said or not? And from the off to the triode. This one is also from the off to the triode. But this one, I want it to be what? In saturation. This one, I want it to behave as a what? As a constant current source. Clear? Okay. I want you now to tell me, before I show you the detail, I want you to tell me, can we look at this diagram? This is the input, VLO. By the way, the output, this switching case, it will be what? It will be based on which frequency? At what rate? At what rate these will be on and off? At the rate of the LO. At the rate of the LO. This is the VRF. Are you following me or not? This is the VRF. Which is what? Which is the sinusoid. Coming from where? Either from the LNA or the output of the image reject filter. Did you get this or not? Okay, good. Now, what is this? Can you tell me what is this? You can see that there are what? Two waveforms. One of them is this direction. The other one is what? Opposite direction. Why? Because the polarity is what? Changing. One time the current is coming here. By the way, when the current comes in here, what is the current here? Zero. Do you understand that or not? A zero current here. And vice versa. So what do you have? I want you to see this. Do you see this one? This, then what? This, then what? This, this. Yes or no? If you add them, sorry, not add them. If you subtract them, why subtract them? Because you are taking what? Differential output. Are you following that? This is what you get. This is what you get. Can you explain to me what is this? First of all, is it at the IF? I want you to see the frequency of this and compare it with the RF. Is it much lower? Is it supposed to be much lower? Supposed to be much lower is the IF frequency, whereas what? Whereas this one is the RF frequency. Clear? Where did this come from? One more time. By subtracting one from the other, you get something close to this. In reality, you will get some harmonics with it. But this, I'm just showing it to you. By the way, even this one does not look like a pure sinusoid, does it? Look at it. Does it look like a pure sinusoid? Does not look like a very pure sinusoid. You have to remember that there will be what? There will be some, there will be some distortion. Now, I will get to the detail in just a second.
The time is 3 o'clock.
Can you explain to me where is this equation coming from? IRF is this. That's the constant current source. That's what I want to be what? The constant current source. Can you explain to me where this came from? This one is the biasing current, which is the DC current. Where is this one coming from? This one is behaving as a transconductance. So the input voltage is V, the output is what? The output current is what? A GM3. GM3 is for this times what? The RF3. This current is going to go either this way or what? That way. And this current, the total current, will go either this way or that one. Did you get this or not? Yes or no? Now, I want you to see, before we get into the analysis, I want you to see something here. Answer me a series of questions. First of all, do you see the voltage gain? Is there a gain? Depends on what? Depends on the GM3 and the what? And the load resistance. So you can get a gain. Did you get this or not? You can get a gain easily. Did you get my point or not? Okay. Now, explain this one to me. By the way, what is this? GC. GC is the effective transconductance. Why did I multiply GM3 by 2 over pi? Can you tell me why did I multiply GM3 by 2 over pi? Because when I'm talking about the current, I'm talking about what? The sinusoidal current. So this is switching effect between what? 0 and 1. Well, the fundamental component is how much? It's 2 over what? Pi. Did you get this or not? That is the effective transconductance. Now, let's understand this and then we'll go to the analysis. Let's get this one, by the way. This one, I want you to see this one and tell me. You understood what this is? This is this. This guy is behaving as this. Okay. What is the current here? We just talked about it. I bias plus what? IR. Can you explain to me this equation? Where did it came from? Can you zoom in, please? More. Thank you very much. I'd say just momentarily, I will ask you to zoom back, but can you explain this equation? I'm still waiting. This is the output current in one of the transistors. What is it equal to? 1 plus sine. What is this sine? This is not SIGN. This is the what? The signal function. Sine is what? Positive or negative? Cosine omega LOT. By the way, what am I assuming here? I'm assuming that it's a sinusoidal. I told you a moment ago that most of the time it's what? It's square. But even if it's square, it means what? The positive side. If this is the positive side, the sine of this divided by what? 2. I'll ask you why it is divided by 2 in just a second. Times what? I bias plus IRF. Did you understand why am I dividing by 2? Why? The current in here is the same as the current in here. There is no current comes in here. You follow me or not? So this term has to be, the sign has to be equal to what? 1. And I have what? 1 plus 1 divided by what? 2. And that's what? 1 times this current. Clear? Clear? Cannot hear you. Now, how about if this one is negative? What is the current here? 0. Where is the current then is going? It's going to go this guy. Did you understand that or not? And one more thing before I ask the operator to zoom back. Do you understand this? 1/2 VLO plus, 1/2 VLO minus. Did you understand this? That's the differential input that I was telling you about. Clear? Now you notice one thing is that only the local oscillator is applied as a what? As a differential input. Whereas the RF is not applied as a what? Differential input. The RF goes only to the what? Can you zoom back now, please? Thank you very much. The RF is only going as a what? As a single input. Single-ended input. Did you get my point or not? In a minute, we will see a superior one than this one is this one. Let's see if you can help me before we get into the detail. We'll get to the analysis. Is this one. What can you tell me about this one? This is, by the way, this is the most widely used mixer. It's called the what? The Gilbert mixer. The Gilbert mixer. How many of you took 448? 448? None of you took 448? Okay. I'm not sure if you do this in the lab or not. But I want you to tell me, before we get into the analysis, can you tell me what is the difference between this guy and this guy? The RF is also what? Differential. In other words, in here, both ports are what? Differential. Now, keep in mind one more time. If the LNA is single-ended, then you need a what? You need another balloon. Did you understand? You need another balloon to what? To generate the differential inputs. Clear? Now, we will see the difference between this one and this one. By the way, I want you to think about this as what? As 2 mixers in what? In parallel. This one and this one. We'll get to this in a minute. Can we get back to here? Where? Can we get back to here? Okay, let's get the analysis before we get to the chart. Let's get to the analysis first. Okay, so now what do I have? What do I have? One more time. Okay, did I miss anything here? Maybe I missed something. VLO is large symmetrical wave switching on-off the coupled transistors M1 and what? M2. Several harmonics of the LO contribute to the what? Mixing. Why several harmonics? Why? Because it's a square wave. Okay. Differential output is preferred for higher gain and more immunity to what? RF to what? IF throughput. What does that mean? If you are going to take it from here to here, you will see that the RF component will what? Cancel out, not the LO component. Can you tell me why the LO component remain? Why the LO component remain? In other words, is this double balance or single balance? Why does the LO remain but the RF get canceled? If you see that there is a constant term in here, that constant term is what? Is IRF. Did you get my point or not? Well, let's get to the analysis in just a second. Let me see if I miss anything here. So differential output is preferred for higher gain and more immunity to RF and IF feed it through. Do you understand what do I mean by feed it through? Feed what through? It means what? You are not going to get mixed. The RF is not going to get mixed with who? With the LO. It's just going to go through the IF. Are you following me or not? Okay. You do understand that this one might cause problems if what? If you do have two undesirable, two components, it happens to be interfering, it's close, and they are both what? At RF, and they would what? Feed forward, and because of the linearity, non-linearity, it results in what? Results in intermodulation that might affect the what? The DC stuff. Clear? Okay. Now, so major drawback is again the high, low, LO to IF feed through. I will show you that in just a second. Resistive loading here, this is sketched as a resistive loading, but most of the time they replace the resistive loading by a what? By an LC tank circuit. Are you following me? An LC tank circuit. And what do they make it? LC tank circuit tuned to what? Tuned to the IF. Do you understand that or not? By the way, with the tuned tank circuit, you are also going to increase the what? You increase the gain also as well. Clear? Okay. The downside, of course, is that what? Is that you might need what? A large LC. Why? Can you tell me why? For down conversion. For down conversion, which means what? At the receive. Remember, a mixer is needed for both what? Uplink and the what? Downlink. This one is telling you what? It might, for the downlink, might require what? LC to be a little bit high, which means what? You need more space on your circuit. Why? Because the frequency is what? Low. Yes or no? And the frequency, remember, it's what? Proportional to what? 1 over square root of LC. So if the frequency is low, the LNC is what? It's a little bit high. Clear? Oh, let's get to the analysis. Let's see if you can help me here. Where did this come from? First of all, what is this? This is the current, the total current, which is what? RL bias. Can you zoom in, please, a little bit? Okay, thank you. What is this? But I'm sorry, I said current. This is a voltage. Do you agree that this is a voltage? Why? It's RL. This RL. Where is this RL? RL. Huh? RL times what? I bias plus what? RL times what? The IRF. Yes? But the IRF is equal to what? GM VRFT. Why? Because this one is acting as a transconductance, constant current source. Agree? But why am I multiplying it by this? What is this, first of all? What is this? That's the Fourier series of what? Of the square. What square? The plus or minus. Not the 0 and plus. It's plus or minus. Did you get this or not? What do you notice in here? You notice in here that you are not getting any what? You are not going to get any DC from here. Yes? Okay, so you are going to get what? What does it mean? When I say there is no DC here, what does it mean? It means this term will not be multiplied by what? 1. Yes or no? By the way, you notice what is the key word I use? Will not be what? Multiplied by 1. Which means that is why we call these types of mixers a multiplier-based mixer, as opposed to the other one, which is the nonlinear device, where we put the what? The RF and the LO in what? In series to be added. Yes or no? The nonlinear is because of the nonlinearity in the system itself. Did you understand what I just wanted? This is behaving as a what? As a multiplication here. Okay. Explain to me one more time. By the way, when K is what? When K is odd. No. When K is what? Even. What is this term equal to? 0. Why? Why? Because this function is a what? The square wave, it only has the what? The odd harmonics, not the even harmonics. So what do I get? 4 over pi cosine omega LOT. This. Do you understand this? Multiplied by what? This. Did I mess up? Did I mess up? Okay. Now when you multiply this term, do you see this term? When you multiply it with this, what do you get? You get the LO at where? At the output. Did you get my point or not? You will not get this at the output. This, you will get it at the output. Not sure, did you get this this? Are you following me or not? You are losing me here. Okay. Let's one more time. This is the B out. What am I multiplying this? This by this, which is what? 4 over pi Li r Li bias cosine omega LOT. Yes? Then what? This, the same term. Sorry, this times what? This, which is what? 4 over pi GM RL. Where is over 2 came from? The cosine. Yes? ARF, which is the what? Which is the amplitude of the what? Of the RF signal. Yes or no? By the way, what happened to the amplitude of the LO signal? The amplitude of the LO signal. The amplitude of the LO signal, I'm assuming that the LO signal is a what? A square wave between what? -1 and what? And 1. So you are multiplying it by 1. Did you get it or not? Losing me? You're losing me? I don't know. I don't know. When I see faces like this, why is this one a function of T? Why is this a function of T? That's the modulation. Yes or no? What is this? That's a phase modulation. That's a what? Amplitude modulation. It's not a pure sine wave. That's why assume what? Assuming a bandpass incoming signal. Do you understand what a bandpass incoming signal means? Means a signal that is centered around what? RF, but it has the what? The spectrum around RF. That's what is referred to as a bandpass signal. Is this a component I'm interested in? There's the component I'm interested in. Am I interested in this? No. How about this one? I want you to see RL I bias cosine 3 omega LOT. Am I interested in this one? This one will go to the output, the third order. Yes? Not third order, I'm sorry, the third harmonic. But it is way too what? Way too high. Are you following me or not? Way too high. Did you get my point or not? Yes? No response. Yes? In addition, what else? What else? Why do I don't care about this one anyway? This one, the amplitude is what? 4 over what? 3 pi. Whereas this one is what? 4 over pi. This might cause trouble on what? On the subsequent stages. If what? If they don't have enough. In other words, it might saturate the subsequent stage. Whereas this one is 4 over 3 pi. 4 over 3 pi is roughly what? Is roughly 3 pi is what? 10.4 as opposed to what? As opposed to 1. Which means what? This one is almost what? 3 times as big as this one. Yeah.
Isn't the passband filter will get rid of all of these except the
What bandpass filter?
after the mixer?
Yeah, but this one is what? We are talking about what? Is there a possibility that the local oscillator, is there a possibility that the local oscillator is close to the IF frequency? There is a possibility that it's close to the RF frequency. Now, if you are going to put a sharp, by the way, that filter is what we refer to as what? The channel select filter. Are you following me or not? It's the channel select filter. I need to make sure that this channel select filter has a what? Has a narrow bandwidth. But that's the trade-off that we talked about earlier in the semester, remember? Between the what? Between the image rejection filter and the what? The channel select filter. We already talked about this. Clear? Okay, good. Did you understand it or not? Where is the LO term in the output? Can you tell me where is the LO term? This is the LO term. All the others are what? Are not. Now, how do I calculate the conversion gain? This is the fundamental. Yes? So, what is it? It's 4. Where is it? Where is it? Did I mess up? It was written somewhere here. 1 second. No, so not written somewhere? Oh, maybe it's in my notes. Sorry. Hey, here. The voltage conversion gain is what? It's 2GM R over what? Over pi. Where is that? 2GM R L over what? Over pi. Did you get my point or not? Yes or no? Notice, by the way, when you talk about conversion gain, if the input has modulation in it, like this case here, you take the what? The peak value of the envelope. Did you understand that or not? You cannot say what? If there is amplitude modulation, you cannot just say what? A square. You need to take the what? That's what we refer to it as what? As the power, the peak power in the envelope. Do you remember this or not? There was one homework problems or something like that. Yes or no? So keep that in mind. But it's not always that you would have a what? You would have a modulation on the amplitude. Most of the time you will see that the modulation is on the phase. And what is it? Once it is on the phase, does it get into the picture of calculating the power? Does not get into the picture of calculating the power whatsoever. Oh, now, before we get to the, by the way, all of this, I just explained it to you, but I thought that I will go over this because it is, clearly written rather than this one. I think you can read it on your own. I don't need to go over this again. But anyway, I will see if I missed something here. I want to make one point here before we get into the other issues here. What do we have here? Double balanced. Yes? I wanted to see. Where is the RF? This is the RF. I have what? 1/2 VRF. This one is what? 1/2 VRF. No, this is a typo. No, there is no typo. I'm sorry. The minus is here. No, this one is a typo. 1 second. This one is minus. Yes? This one is minus. But this one is okay. Why? Because these are back to back. Did you understand that or not? This one is what? Is 1/2 BLO minus. This one is what? 1/2 BLO plus. 1/2 BLO plus. Clear? No response. Clear? Okay. Now, one more time. This is the biasing current. This is the bias current. This one is also still behaving as a what? Behaving as a what? As a transconductance. However, the current is either going this way or it's going what? That way. It's not going to go both ways because either this one is what? If this one is on, this one is what? Off, and vice versa. Did you get this or not? Now, if this one is on, let's assume this one is on. This one is on. What do I want? What do I want? How am I going to get the output? From where? By the way, look at the output. Where am I taking the output? This is the output. Which is what? Which is from here and from where? From here. Did you get this or not? From here and here. Or it is the same as saying what? From here to here. This point is the same as this point. Same voltage. This point is the same as this voltage. Did you get my point or not? And from here, I am taking the what? I am taking the output voltage. When I say V out means what? This. VIF. Clear? Now, answer me the following question. Why will the LO be cancelled? The LO, the VLO. Remember in the previous one. Let's get back to the previous one. Where is the previous one? Here, this one. The I bias, yes? This term, which is the constant term, was multiplied by what? By the fundamental component. Sorry, by the constant. No. This is the constant term was multiplied by what? By the fundamental component here. So I got the LO. Yes? Why is it gone here? Why is this one, it says no LO harmonic feed through? Why? Because in here I'm taking what? I'm taking the difference between this one and this one. Did you get my point or not? So the LO will also be what? The LO will also be cancelled. Both the RF and the LO will be what? Will be cancelled. Clear? Clear? This is what is referred to as what? As the Gilbert mixer. 1 second. What, did I mention this? No, it's not mentioned. Mentioned, please. It's called the Gilbert. Again, after the person who designed Gilbert mixer. Answer me the following question. What is the, by the way, let's write the equation. Let's understand the equation first. V out is the V out equal to what? Again, by the way, I'm assuming that in the equation, I'm assuming this is what? Sinusoid, just for simplicity. Sine, cosine omega LOT. Remember, when the sign is positive, what does it mean? Cosine omega LOT times what? RL over 2 of what? I bias plus what? GM VRF, this is the RF current, minus the sine of what? This term, minus. Why is it minus? One more time. So because I'm taking a difference from here to here. Minus sine, signum. I keep saying sine, I'm sorry. Signum. Omega LOT times what? RL of T. 2. Why is this one minus? This one is minus because the VRF is also what? Is also double-ended. Did you get my point or not? This one is a plus. Sorry, this one is a plus. This one is minus. And then there is a minus between them. If you do that, you will end up with something like this. Which is what? The signum of what? Cosine omega LOT times what? RLGM VR of... 1 second. I messed up. Oh, sorry. This is GM times what? VR of T, which is what? Which is the current. This is the current. Did you get this or not? Yes or no? Okay. What is the good, what is the not so good about this? What is the good stuff? What is not so good stuff about this? Now, first of all, I want you to understand why does this one generate less even order distortion? What even order am I talking about? When we say that the RF is not going to be what? Leaked. Are you following me or not? Yes? It means what? When it says even order distortion, even order, either the even order harmonics or the even order intermodulation components, it's less because there is a what? There is a cancellation in here. Did you get my point or not? Any noise in a common mode, will also be what? Will be also cancelled. Common mode means what? Applies to both. Do you understand that or not? Better linearity. But on what expense? On the expense that this one will draw more what? More power, more current. Are you following me or not? And takes a little bit more what? More space because you do have multiple transistors. Clear? Clear? But most of the mixers are designed that way. That's the basic concept of what? Of the MOSFET, the double balanced MOSFET filter. This one, by the way, is a comparison between the two. Clear? Okay, how many transistors did we need here? 3. In here, how many do we need? 1, 2, 3, 4, 5, 6. 6. So it has been doubled. Are you following on it? And again, as I told you, the R1 and the R2 usually are what? Usually, it's a tank circuit, approximated by a tank circuit. Notice here it says a little bit of a small feed through. Small feed through. Why? If they are not matched properly, they are not going to be what? Canceling each other exactly. Did you understand that or not? But so there will be but a small value depending on what is the current, the I1 and I0. Clear? Now, before we get into this, let's go back to the notes to see if I missed something here. This is the concept, you know, the switch. One on, one off, one on, one off. I explained this one to you. By the way, look at this one here. I want you to see this. Let me see, do I have a chart here? I want you to see this. Just this one. Is this a switch? This is a switch. What is the input? RF. You agree? This one is what? On, off, on, off. Based on who? Based on the LO. Did you get this or not? Are we going to get IF at the output? I'm not sure. Did you get the idea here? Did you get the idea here? This is called what? Passive switching mixers. We already talked about it. But I just want you to understand it. What is the output here? The output here is what? Is VRF times this. This one can be what? Expanded in a what? In a Fourier series expansion. And one of the terms will be what? Will be the IF term. But this one here, by the way, when you see this one, you need to understand what this one is missing is that there is a what? A filter in here. After a mixer, there always a what? There's always a filter to filter out any of, you can read the equation, this is the equivalent circuit as well. By the way, what is this? This is the noise model. Where is, let's see if you can help me with the noise model. Where is this from? This is the source. Yes? Where is this from? This is when the diode, when the switch is what? On which mode? Triode mode. Yes or no? It's behaving as a resistor. What is this? This one is the noise voltage represent. In other words, is this noiseless? Yes or no? Okay. What is this, by the way? This one is the noise that is provided by who? By the load, which initially we always neglect this one, but here also is there. Did you get my point or not? Yes or no?
Professor?
Yes.
5 minutes left.
Oh, okay, okay. What is this? First of all, look at the chart. Passive sampling mixer. Sampling. What does that mean? This is VRF. Again, this one here is what? Is on off. But what am I using here? To what? To hold. This is a sample and hold circuit. Whereas this one, you see this one? This one is a resistor. You lost me here? You lost me here? How do you change the analog to digital? What is the first step? The first step is sampling. Yes? Excuse me. What is the next step? Quantization. But in order for the quantization to take place, you need the sample to remain what? To remain there for some period of time. You are not going to quantize it on the fly. So what happens? You are going to put a capacitor in here. The voltage here, this one will retain its what? Will retain its what? Its value until the what? Until the next sampling interval. Yes? What is this one is generating? What is that? That's the envelope. You are not getting it? That's the envelope. Do you understand that or not? And the envelope is a what? Is a low frequency components. Low frequency, which means what? I have down converted the analog, the RF into the what? Into the IF stuff. Mixers comes what? In different types of shapes and so on. So by the way, you can analyze this by assuming that this one is what? Is an ideal sampler. An ideal sampler. Yes? And then you hold, you get what? You get this, and so on. So clear? This is the sampling of the RF signal. You are multiplying it by what? And you are by the way, when you are holding it, what does it mean? You are applying it to a filter. Yes? With what? What is the impulse response of the filter? The impulse response, not the frequency response. The impulse response of the filter is what? Because remember, the multiplication is done in which domain? The multiplication is done in which domain? In the time domain. Did you get this or not? Yes? And I want to hold the value of the sample for what? Until the next sample comes. Which means, what is the, for the zero order hold, what should it be? What should the impulse response be? It should be, it's a trait. Did you understand that or not? You are losing me here. Here, this one. This one. Dum, dum, dum. You are holding it. Yes? Which means, what is the pulse shaping? What, by the way, what do you get by convolving? Listen to this. What do you get by convolving an impulse with a filter whose impulse response is a square? You get to what? The impulse shifted to where the square is. But the impulse is what? It's gone. You end up with what? Just a square. That is what? Holding the value of the sample until what? Until the next sample comes. Did you get my point or not? This is this one. This one. Clear? Clear? Okay, good. Now, let's get back before I run out of time. Did I miss anything here? This is, by the way, the switch action. You can see it on your own. You can read the derivation on your own. I strongly encourage you to read it. This is the what? The LO to the IF and the RF to the IF terms. This one, by the way, I want you to see this. Tell me, what is this? Is this balanced or completely unbalanced? This one is completely unbalanced. Why? Because I am taking the output from here compared to who? To the ground, rather than what? Rather than one that I showed you, which is taking the output from where? From here. In other words, this is the one that I'm showing you here. Here, this one. It's a what? Single-ended, rather than what? Differential output. Did you get my point or not? In this case, if you follow the analysis, you will see you will get both what? LO term and the what? RF term at the output. Can you tell me why quickly before I run out of time? Can you tell me why the RF also will show? Because the gating function is no longer what? Plus or minus 1. It is now what? 0 and 1. So you will get a DC term from that as well. Yes or no? Okay.
Professor?
Yes.
We just ran out of time. Sorry about that.
Can you read this on your own, please? This is all I explained it to you. But this one is just showing it to you schematically. Can you read it on your own? And let me know if you have any questions. Because next time I want to start with the oscillator stuff. Can you read this on your own? Okay, good. But I will be posting it so that you just download it.
And this concludes EE 544 with Professor Ali Zahid on Thursday, April 17th, 2014.